Thank you. Thank you for having me. Thanks for the introduction. Also, if you haven't seen, we had 3 technicians, and the reason why the beamer didn't work was because a power strip was not turned on. It's always the easy things.
That's why you need 2 PIs.
It's also now I don't have my slides here, but so excuse me if I sometimes turn around to see what I'm actually talking about. So a little bit more about my background. I started my research career in malware analysis back in 2010. Because I always thought this is the most interesting area where you can do program analysis because it's the software that's most obfuscated, tries to detect the analysis environments, and it's just the hardest to analyze. But over the years, I've more and more moved towards analyzing mobile applications. And now the clicker also isn't working. Perfect. Okay. So controversial opinion, malware on mobile devices isn't that much of an issue. The way the distribution system works on mobile devices with the app stores, they're doing actually a pretty good job of keeping malware out of the stores. And then even if there's malware in the stores, you don't have drive-by downloads like you would have on a desktop computer, or malware exploiting vulnerabilities to infect devices. Malware on mobile devices mainly needs to get users to actually install stuff. But if you look at all the apps that you have on your device, there's a lot of other different types of apps that have very interesting permissions, interesting functionality, very critical functionality. If you think about banking, all your messaging you're doing, shopping, essentially everything you do in your daily life, there's an app for that. And you expect an app on your device to handle your private data and interact with all kinds of services. So over the years, those are some older and some newer news clippings. There are still issues where people find interesting security critical bugs and behavior in apps on the store. And on the one hand, the Google Play Store and Apple do a somewhat reasonable job regularly cleaning out the stores and kicking out apps that are against their policies. And they have cultivated this perception of this walled garden. If you install apps from our stores, you're going to be safe because we are policing and we're checking whatever app is in our store. But if you look more closely at the developer agreements, Google says we actually don't have any obligation to monitor the apps we are providing in our stores. So it's up to the developers to make sure that whatever behavior the app has, that it's complying with laws and expectations of users. Apple is a little bit more verbose. What I find nice, Apple also somewhat recognizes that it's actually for a developer pretty complicated to figure out how to make your app compliant with all kinds of regulations around the world. But essentially, both of them present this walled garden. They're telling us now that Apple has to provide other stores besides the official one. They essentially told us that's the apocalypse, like users won't be secure anymore if we give you different sources than our official one. But on the other hand, they also don't have any responsibility to check what's in their store. But developers, on the other hand, have. This is just a very broad overview I found on a lot of countries in the world nowadays have some form of regulation in terms of privacy, also upcoming in terms of security of what digital products should comply with. The main regulation that's been around for a couple of years was the GDPR. And I was very excited in the beginning when GDPR came around, like finally a win for user privacy and something is happening. The reality was a little bit more frustrating because the end effect was every app has now this long privacy policy that's not necessarily written for users, but written by lawyers, for lawyers to cover all kinds of behavior that you could have in your app. And this is a very nice art project where an artist tried to show how ridiculous this privacy policies can actually become. So a better way to present this information are the privacy labels and the safety labels. This is also a development in the last couple of years. Apple introduced these privacy labels where every app that's in the App Store needs to, in some condensed form, visualize the kind of data they're sharing and with whom. Google has a slightly different approach. They have the data safety section, but also where developers can specify how they're processing users' data. But what's interesting about both is, again, if you look at the fine print by Apple, they're saying they don't monitor the information hasn't been verified. The developer can say pretty much anything. Google, on the other hand, has this independent security review, which sounds interesting at first, or it's actually kind of interesting. But if you look at the details on how this works, they've built with some industry players this App Defense Alliance, and essentially they've taken some mobile security testing guides from OWASP, put them into some guidelines and checkboxes that you can check apps against, both for Android and iOS. And then there's this list of 6 different companies that are the official testing labs that are allowed to do this independent security review for your app, which is a somewhat nice development, a step in the right direction. One big issue is if you look closer at the testing guidelines, there's a lot of them. Some of them can be automated. A lot of them are also just manual pen testing, essentially, of the app. So for every app release, you need to do, again, this manual security verification with a third party of your app. And if you think about smaller developers, especially for them, that can be a huge burden. On the other hand, what's also interesting on the bottom here, they also give security recommendations where we as a community are not quite sure, is this actually the right way to go? So a couple of years back, we wrote, 2 years back, we wrote a paper about, is this advice of certificate pinning, is this actually the right way to go? And we also found a lot of apps don't implement this anymore because has some security benefits, but on the other hand, it's super hard to maintain and might not be something you want to have on this checklist for your security review. Yeah, there's some more interesting stuff. Also, in the middle, there's these 2 innocent-looking boxes that say check third-party libraries for vulnerabilities, where the guidelines essentially tell you, yeah, go and reverse engineer this SDK or library you include in your app, so you can make sure that any third-party code doesn't have any vulnerabilities or privacy issues. Again, largely a manual step. So how do we solve this? And what I want to do is essentially automate a lot of these processes, and I've been, again, working back in the days on malware analysis and now working on automatically analyzing applications, running them in an environment, and figuring out what they're actually doing. As our motto often is, PCAP or it didn't happen. So the nice thing, if you're running applications, you observe the network traffic, you see which kind of data is going where, you kind of have this smoky gun where you can say, it's not that the code is there that could do something fishy, but we actually see it in the wild. And with this interactions and triggers, we know how to trigger certain behavior and have the essentially evidence that it happened. And the ultimate goal would be, if we're taking these privacy labels that are in the App Store, that we have an automated way to verify if this information that's in there is actually true. We're not there yet. We started with a very small project on iOS, but also with some interesting results, like a master student built this test harness where we tried to figure out for some identifiers, is this what we see in the network traffic, what's in the privacy labels? And I think the most interesting number is for a quarter of apps, the privacy label set did not collecting any information, but then if you look at the network traffic and the system access we observed in our test environment, they still did. So there's also some more work to do. And maybe as an overview of what this pipeline looked like, what we did for analysis, essentially, there's a lot of moving parts and also still a lot of parts that we need to improve. Even getting apps from the app stores sometimes can be really hard because they're not designed for researchers downloading millions of apps they have in the store. But our pipeline essentially was crawling the store for the apps and the labels, installing the apps and preparing the research, our research device. So we're running analysis on real phones that you have to wipe after every analysis run. Then we typically have some dynamic analysis framework like Frida that hooks different system call APIs and also tries to trigger some behavior. There's the monkey, that is the standard testing tool that we still use that just clicks on the user interface and tries to simulate user interaction. It's not perfect. That's also one big step that we still need to figure out. And then, yeah, ultimately look at the network traffic to see what kind of data is being shared. So today, I'm not going to talk about the whole general pipeline where I said there's still lots of moving parts, things to improve. But I selected 3 different projects or different areas that showcase interesting findings we had and also interesting problems we already at least partially solved. And the first one is, how do we even in network traffic, for example, identify what's private information that's being leaked? The second is, how do we deal with applications that don't work in isolation, but applications that are companion apps for all the kinds of smart devices we have in our home and offices and kitchens. And the last one is, how do we deal with apps that are not developed in a traditional sense, but basically web interfaces to different web services. To start with the first one, again, so we have this army of phones in our lab. We're running our device instrumentation, and we're looking at the network traffic. So what are we looking for? If you see an HTTP request like this, so the easiest thing is you can check if it's HTTP or HTTPS. And then you start looking at what's the kind of device identifiers that's in the traffic. I think we started 2015 doing this kind of stuff. One of the still state-of-the-art techniques here is just do basic keyword search and regexes and look for identifiers like the phone number, the IMEI number in different transformations. It kind of works. I think we could do better. One of our first attempts to do so was recognizing that it's not only about the device identifiers that's in the traffic, but the structure of the whole HTTP request. So we started training a machine learning classifier because that's what they're good at, finding patterns. And that's also partially what we're still doing today, training a classifier based on manually labeled HTTP requests, where you then don't look for specific phone numbers or names, birth dates, whatever you're looking for in the traffic, but more looking at the structure of the request and which kind of keywords are used for, and parameters are used for transporting certain information. Which works well for if you just have text-based data, but then one of our next projects was, maybe a little bit more detail. What we did for this project was also getting user feedback. In a sense, one scenario in which we're doing app testing is in the lab, where we're just trying to figure out what apps are doing. Ultimately, it would also be nice if users could run some of our techniques and get more visibility into what their apps are doing. And we had a small study with 100 users that routed all the traffic through a small Raspberry Pi that intercepted the traffic and then showed the users what the kind of personal information that we found, and the users had the option to give us feedback, again, also to train our classifier to see if what we were finding was actually correct. And ultimately, a nice also benefit that operating systems could have more of is giving the user the option to block certain type of information or also modify some information. Sometimes it's not necessary for the app to have your precise location. Sometimes the app just needs to know that you're in the specific city. So that was also one proof of concept where we were hoping that how this could be implemented. And we also used the system for a more longitudinal study where we wanted to see, we've been analyzing this for a while, is privacy getting better, or users are getting seemingly more aware about privacy? What are apps doing? Are apps protecting different types of identifiers better over the time? And on the left top corner, you see different types of device identifiers, where we actually saw improvements. So on your phone, you have some identifiers that are persistent, like the IMEI, that you can change. Like you can throw away the phone, get a new one, then the identifier changes, which is really bad for privacy. What we want to have is more like the advertisement ID, where users can go to the settings and reset their privacy profile essentially on demand. And on the one hand, we saw, yes, at least the use of these persistent identifiers got better. On the other hand, we also tried to aggregate the amount of different types of data points that are collected by users. Here you see with the sliders, that was a proof of concept for users where they could play around with also weighting their preferences, how critically they saw different types of information, so we can get somewhat an overall score for them. Is this version or this app more privacy invasive than another one? And the third dimension that we looked at is on the lower left, where in terms of privacy, like as a user, some information needs to go to the first-party developer for the app to function. But then a lot of information is also going to third parties, which you might not want to have. And when we looked at this, how is information distributed between first and third parties, what was interesting, Pinterest is the most high-profile example that we found, but simple software engineering bugs. And in a sense, in some Pinterest versions, they just started sending the password to a debugging library where it shouldn't go. And Pinterest was the most wide-known example, but it's just was an interesting finding we actually didn't necessarily expect. In this case, so we didn't do a developer study, but for all the stuff we found, we notified the developers and told them what was going on and gave them some recommendations. Got some nice feedback. It's always nice to hear that developers were actually very happy that we found this kind of things. We also got some more frustrating responses from a security person's perspective. One was that they just sent the password in plain text because they needed to support some old legacy system somewhere that couldn't handle any encryption or anything, or just the apps that we are a messenger app, but the app description doesn't say it's secure, so why should we care about any security? And I think the last one was also very depressing in a sense. Nowadays, every web service and every system needs an app. Not every company has the resources to build an app, so what you do? You outsource the development of an app to a third party. But what do you do if the third party goes out of business? Then you have this old app where you can't necessarily fix any issues anymore. Yeah. Sometimes our work is also very depressing, just showing what's going wrong, but now I can transition to the next project that was also very fun to do. So in the beginning, we looked only at textual leaks, like how do apps handle text-based private information? But there's this rumor going around that Facebook is listening all the time in our pockets to whatever we're saying. And we wanted to build a system where we look for how apps are using audiovisual data. Like, are they recording and sharing audio, videos, photos? And we prepared our test environment with some honey images and instrumented the apps. So we took pictures and photos on around 30,000 apps from the Google Play Store. And what we found is there were a lot of images in the network traffic. We really thought that we would find something about Facebook, but the far biggest thing we found were these photo filter apps. That there's ton. I'm not sure if they're still popular, but they were the thing a couple of years ago where you can make your face older, younger, put on makeup, whatnot. You take a selfie and let this app do the magic. And you would imagine this app is doing some machine learning magic on your device, but ultimately, no, this app sends the photo to a server somewhere, essentially gets the copyright, royalty-free, fully paid worldwide license of your photos. Oh, and this one also sends it over HTTP, so it's nice if you're in a coffee shop and just sniffing the Wi-Fi to see all the pictures that other people are taking. This one didn't get much attention, but there was a second one, the Face app. Somebody else, so we didn't go to the press about this, but somebody else picked it up that Face app is actually a Russian app. And in the US, some journalists and people weren't quite happy about the thought that Russia now has a huge database of selfies of a lot of American citizens. I think the app is still around. The only thing that changed is previously in the App Store, you had this, as the developer contact, an address in Russia, and now they changed it to some post box in the US. But essentially the point is this, like, we would think those apps are really smart, but then of course it's also in the interest of the app to collect photos. We've also seen with other issues, those photos are also great for training machine learning models. So of course, if you have an app that takes a lot of pictures, it's a valuable data set to collect. That were the photos, but we also found other things. I'm not sure if it's readable, but this issue of screen recording apps. So this is a screenshot of, I think, the Air Canada app, where you put in your billing information and your credit card information. But what we found, those apps send screenshots of everything you do with the app to a third party. It's a nice service for developers. So developers try to figure out how users are interacting with the app, where users are clicking, to improve the app's user interface. But on the other hand, sending every screenshot while users are inputting sensitive information, passwords, messages that they're not sent to a third party, I don't know. The thing is, it was also not in the privacy policies. Nobody talked about that the services existed. This also got some really nice press attention. It's maybe a little bit actually more alarming than it should have been. On the other hand, Google's response was a little bit not sad, but expected. So we talked to the developers, and we also talked to Google that, hey, there's these apps in the store. Do you want to do something about it? They gave us this vague phrasing that we put in the paper that they took the appropriate actions. And it was essentially GoPuff and Epsi were two concerned apps. They now have a line in the privacy policy somewhere that nobody ever is going to read. But we also talked to some developers that actually excluded those libraries from their apps because the benefits for them from a usability point of view were not worth the privacy invasion of the users. But they weren't aware before what the implications of the services were. Okay, then the third and last project in this area, taking back a step a bit from images, again, back to text-based information sharing. So we look at network traffic. We try to figure out what kind of personal data is in network traffic. But if you look at this big blob of data, it's hard to figure out what's going on. And it could also be that developers are trying to obscure information to keep it from eavesdroppers that observe the network traffic, or from regulators, you don't know. But this was an example we found and reverse engineered that there's this weird, they do a hash of some identifier, then they XOR it with some key, and then they encode it and send it over the network. And with any conventional technique for app analysis so far, this is super hard to find, or even impossible to find. So our idea in this project was, I think, very simple, but also very elegant. We did black box differential testing with the key idea. We don't want to know anything about the app. We just want to execute the app, instrument the environment around it in a limited way. But ultimately, if we change some private information on the device, like the IMEI, if we run the app multiple times, we see changes in the output. We know that the changes in the output depend on the private input information, even though the output information doesn't make any sense. And doing this, so it sounds easy. There were a couple of things that made this more complicated. Ultimately, network traffic is messy, non-deterministic, and there's a lot of different variables that make requests change from one time to the other. So you have timestamps in network requests. Network parameters depend on some system parameters, like how much space is left on the device, how much battery you have left, some random session keys, some session keys you get from the server, and also differences in how you execute the app. Even if you try your best, every execution will vary a little bit. So you can't really directly compare different runs of network traffic without some fixing, which we call this explaining the non-determinism by figuring out what are the sources that make our analysis more complicated. We started to instrument the environment and record all the sources that introduce randomness. And essentially starting to run the app, not once, but run the app a number of times, always record the different random values, timestamps, values we get from the network, and building a summary of this is the overall generalized behavior of an app's network behavior. So this is without changing any input information, just running it on a bare device and building this kind of contextualized network trace where we can, after some time, figure out, hey, this is a timestamp, this is a random UID, and just replacing the information with tokens. So that ultimately, when we had enough runs in the end, with the last run, we can start changing private information, and then we know the specific part that now still changes in the output was actually some kind of private information that we then can dig into deeper and in this case, we reversed the apps to really figure out what's going on and verify that what we were finding was actually a private information leak. Maybe some justification why we did this. So what we found is that for 80% of apps, every time you run them, the network traffic is different. There's some random values in there. But after, I think, 5 to 10 executions for most apps, the network traffic somewhat stabilized. But still, for 20% of apps, we didn't know where the randomness was coming from, but we went from 80 to 20%, which is already was good enough for our case. Also looking at, we compared it with different approaches. So Recon was the approach that I presented in the beginning. This was our work. We used the data set from this and looked at what are other data flow techniques. For example, plethora, that's the static data flow analysis technique. And Rubis was our sandbox that did some dynamic data flow analysis to find data leaks. There was some hybrid work. And Recon, previously, we only looked at network traffic. So we really compared different types of techniques, how you could find information leaks. And what we found is that apparently a lot of information leaks are heavily obfuscated. And compared to in 44 apps, we found 270 apps in our data set that leaked some kind of information. Yeah, I'm skipping over the last part, but that were some encouraging results. Going forward, I promised in the second part talking about how we are analyzing apps when they're not only interacting with servers on the internet, but when they're interacting with smart devices that are now everywhere. And there, my favorite example is always these cloud pets. I have the unicorn on the right in my office. I got it for Christmas at some point. It's a very nice present. It's a stuffed animal that has a microphone in there. It has an app to control it. And it was taken from the market after some time because it just had too many vulnerabilities. Does someone have one of those? There's also more. There was some analysis on what these things did. Of course, they sent all the data to a backend that was unsecured on some Amazon bucket, including audio recordings of children. Anybody could do firmware updates of these nice animals. You didn't have to use, or you could just have very simple passwords for your account. Any companion app could, if you're in reach of these devices, could interact with them. And not even companion apps, like just through the API. No, on eBay, you can buy them secondhand too. Although you don't get the app. So the app is also, you can buy the domain they're sending the data to if you want to collect some data. I think we looked it up. It's like 4,000 euros. But the motivation for us was a lot of these issues are either based on the app or we could have found them through the app. And that was a project together with one of your professors, Mr. Bogolte. We actually wrote a whole project proposal in how can we do something about this and analyze this nice Internet of Things. And our main idea behind this is, yes, you have the devices, you have your home assistants, you have the companion apps that control the devices, and you have some internet backend somewhere. And what we are focusing on is this mobile device that sits between the devices and the cloud backends. And we wanted to try to figure out how much information about the ecosystem can we get just by looking at the companion apps. Because you can go to the app stores and just download them and analyze them. This is our first project, IoT Flow. We presented it at CCS last year with the main goal, again, take the companion apps, figure out how they communicate with the devices and with the internet. Also, are they communicating only with the device manufacturer, or are they also trying to get a data that they can send to advertisers and trackers? Because that's what apps do. And also which kind of data is shared. And we did some large-scale analysis on around 10,000 companion apps. So there's surprisingly not that many companion apps out there, but I think we got a pretty substantial data set. And what we did here is the whole approach turned out to be more complicated than we originally expected. So ultimately, We did a combination of value set analysis and data flow analysis. Because on the one hand, we wanted to know, yeah, what are the endpoints and protocols apps use to communicate, but then going back from this endpoints, what is the data that is flowing into these things? And that's the left-hand side of the graph. And on the right side, it's also, we figured out some other issues with traditional techniques in this area, in that Android apps are very compartmentalized and very callback driven between activities and services. There's a lot of intercomponent communication that typically static analysis in this area didn't really factor in. So we kind of used our approach for identifying the endpoints and the data flows to also use them to trace back over the intercomponent communication barriers. And I think in the interest of time, I'm going to spare you the code example where I walk through how this all works. You can check out the paper. So the goal is at the end that after we run our different steps of analysis, we know that the app communicates to example.com and uses data that's coming from Bluetooth, some data that's coming from some IoT device. And the nice thing here is we don't have the IoT device. We can just make some conclusions potentially about the device just by looking at the app. And I think to me, that's also a nice filter in a sense. Once we find the apps that seem to be the most broken, we can then start maybe getting the devices, or at least know at which devices to look at for more in-depth analysis of what's going on. So some findings we had, don't ask me why a smart grill exists, but one of the apps was for a smart grill. Where we also look in terms of GDPR, if you're using this as a European user, is data sent to the US? Yes, it is. Also, in this case, don't ask me what private information a grill connects, but it's more on principle. Those apps were really badly designed. And yeah, the last point, we've heard about Mirai and other botnets. We have so many insecure IoT devices, and botnets could take over a smart grill and just use it to perform denial of service attacks against other infrastructure. And the second one was essentially the smart camera from hell that you wouldn't want to have. It had completely broken authentication and outdated cryptography. It's also, keep in mind that reversing the firmware of the IoT device might be harder, but you can just take the app from the App Store, and if there's hard-coded keys in there for the communication, it's relatively easy to extract, but that's, yeah. And the second bigger picture finding was we got all these endpoints, and one type of protocol endpoints are using is MQTT. That's the specific IoT network protocol, some topics subscribe, publish, subscribe protocol, very lightweight, but also very lightweight in terms of authentication. So once we got the endpoints from the devices, we could connect to them. We had approval from our ethics research board we didn't try to modify any information, we just tried to see if we connect what information we get. And that's also not real information, it was not all -1 something. But essentially for this app, it's a health monitor for heart and lung, and you can connect to the server and enumerate data from different users. And the second example was, this is a smart car dongle that you can put in your car, that you can enumerate the locations and some hardware specifics of different cars. We want to dig more into that direction, but there we get fingerprinting those servers and trying for vulnerabilities. There we're getting into more ethically questionable territory, which is, yeah. Okay, last part. So I talked about PI, I talked about apps that interact with devices. The last part was motivated by, so we are typically analyzing bytecodes in the apps, but what we found, a lot of apps are just glorified websites. So the easiest way to build an app is build a framework around a website and just display it in your app. Which a lot of this analysis I presented before, it's the typical limitation. We can't deal with this kind of apps. But we still wanted to look a little bit deeper into this because essentially a lot of apps are in-app browsers. And also app developers, if you look at Facebook, they want to keep you in their app. Facebook wants you to click on every link that people share and go somewhere on the internet, but they still want to keep you in the app and don't want to move you to the browser. So a lot of apps have this in-app browsers that on Android and iOS, there's different mechanism how you can integrate web content. Some of them have some indication that there's an address bar somewhere. Some of them are just fully integrated into the app where as a user, you don't really see that this is just a website and not native app content. And we looked at all of this together with our web security people and looked at how good are the web security mechanisms implemented in this type of browsers. And one of the most interesting things we found was the Android custom tabs. What's special about them is you have the native application, you embed some web content, but essentially it's a browser window. And the browser window, it's a Chrome custom tab. It shares all kinds of things with the browser on your device, including cookies, any state information about the websites you visited. And it also has nice convenient callbacks to the app that tell the app more about the websites you visited. So that's essentially, we have a paper coming up at Security and Privacy of what are these implications for web security. In a sense, as a developer, you assume your website will be displayed in a browser. That's very much secure, but what if your website is not displayed in the browser, but in one of these components that then is really tightly integrated with an app that you have no control about or don't necessarily trust. And as an example, our student built this recipe app that has this custom tab embedded, and our proof of concept attack essentially was, you have this recipe attack, but in the background, the app just opens hundreds of these custom tabs. The user doesn't even notice, and with every custom tab, the app can fingerprint the websites the user has visited, just based on the state you're sharing with the browser, which is just something that shouldn't happen and breaks a lot of web security guarantees. And also, typical browser mitigations don't work in this regard. We have some mitigations in the paper, and some already have been fixed. But it was also interesting to see that it's not just Chrome. Essentially, pretty much any Chrome-based browser was affected by this issue. Only on Android. The good news is on iOS has similar mechanisms, but it's implemented in a more secure way, in a sense that you don't have a back channel where the app can learn what's happening in the custom tab. So from a design point of view, in this case, only Android is broken. Okay. This somewhat concludes the main part of my talk. I still want to highlight two more recent projects. Again, our holy grail is building this testbed, trying to build a system where you can verify all these app labels and what apps are saying they're doing in the privacy policy, and showing that probably sometimes they do more. And also, I switched it around. Okay, let's start with Android. Not only focusing on Android, but even all the work pretty much all the work in this area is on Android. But Android makes it really hard for us in a sense that they keep, of course, upgrading the way their developers can build their apps, the way apps are executed, which break all kinds of analysis tools that we put together. So you might know that Android apps are built in Java or nowadays Kotlin, and still over the years, we always looked at the bytecode because that's how apps are distributed. So you compile Java into bytecode, and that's what the Dalvik runtime on the Android system then worked with. The thing is, nowadays, Android has this additional step on how they're running and compiling apps, and essentially everything you run on your phone now is a binary. And apps are also not necessarily distributed as bytecode, but as binary code, which turns out to be this huge pipeline of going from the left, from source code, to the right of what's actually executed, with a lot of moving parts, how third-party components are included. And what we're working on right now is how can we simplify the analysis process, but just focusing on the left and the right-hand side. And on the one hand, using the whole build pipeline for analysis, but moving away from all these Dalvik-based tools, which also, for example, breaks the approach we had for IoT flow for CCS. And the other big project, which sounds so much easier than it is, was building data sets. And one of the things I also want to go is directly compare Android and iOS apps. So you can say, if you have the Duolingo app, is it more secure on iOS or is it more secure on Android? And ultimately, also, can we draw some conclusions about the operating systems themselves? Like, what are the security and privacy features on each platform? How effective are they? We took the first step. We have a data set now. And if you have any ideas in this area, we just presented a paper last week on a data set and a methodology on how to collect these apps, how to match apps, how to figure out which apps are the same on each platform. And hopefully we're gonna see finally a lot more iOS analysis out there and also comparative analysis. And with that, yes, we provided artifacts. I also want to do a shout out to a conference I'm chairing. One of the big frustrations throughout my work has been the availability of artifacts getting outdated every time the operating system has a new update or Google changes the way they're developing apps. So artifacts are important. Luckily, we have artifact evaluation at a lot of conferences now. And at Exec, we also have the artifact competition. So if you have an artifact that has been used by a lot of people and you think has a lot of impact, submit it, and we're happy to showcase it at the conference. Still, one of my frustrations was then, yes, we have all these artifacts, but how are we using them? In a sense, in a research paper, if you use an artifact, and sometimes you get this, yeah, but that is not novel. You're just reusing some previous artifact, and what's your contribution? And so this year at Exec, we have this reproduction and replicability track. And I must say, I took inspiration from IMC and SOUPS for this. Because in system security, we don't do reproductions or replications. It's just once a measurement is done, it's not novel anymore. And SOUPS and IMC have started with this. Maybe you bring some different aspects, some different also environment variables in your measurements. There's value in rerunning experiments. I always also get questions if I present about my work. So after 5 years, have you looked at the situation again? But then no, we don't do, because it's really hard to publish studies that look at a problem that has already been published before. So yeah, I hope this will get better in the future. And with this, I'll leave you with some takeaways and hopefully some time for questions.